multiple DES was used in the late 1990s, starting from late 1990s after brute force attacks were successful to crack DES. And the idea is to apply DES multiple times, either 2 times or 3 times. The underlying property of DES makes it possible. In other words, DES is not a group. Now, group is a mathematical concept, but basically what it means here is that there are no, for any, okay, so for any keys, K1, K1 and K2, you apply DES twice, okay, you use K1 first, get a result, and apply DES using K2 first, and then using K1 by applying DES twice. And so you get a ciphertext. Then for any K1 and K2, and you cannot find any K such that applying DES once, you get the same ciphertext. So that means, in other words, for any K1, K2, and K, this inequality holds, okay? So by applying DES once on K is not going to be the same as applying DES twice on 2 different keys. So that you can use this result to do DES several times with the effect of having a much longer secret key. Okay, so for instance, so each secret key K2 is 50, K2 and K1 is 56 bits. So you combine them, it's 112 bits long. Okay, so the general idea is to take M keys and apply DES n times to get NDS/M. So this N and M may not be the same. So common ways to do it is 2DS/2. So you use 2 different keys and you apply DES twice. And you use 2 different keys, but you apply 3DS. You apply DES 3 times to get 3DS/2, or you get 3 keys and apply DES 3 times to get 3DS/3. Each time you would use each time you use a different key. But for 3DES, this is a normal way to apply DES. So you have 2 different keys, K1 and K2. Okay, you apply K1. So you use decryption on K1, and then you use encryption. Okay, this is encryption, this is the input. So you use encryption on K1, and then use decryption on K2, and use encryption on K1 again. So this also 3DES. Okay, the reason we want to do this is to make sure the ciphertext using single DES can also be can also be decrypted using 3DES/2. You just need to make that key using for single DES to be the key K1 and K2. So that way it is still applicable. Okay, so of course, other combinations of END, encryption and decryption, are just as secure, but then the encryption using single DS may no longer be applicable for this other combinations. All right, so using 2 keys to extend the key length to 112 bits would make DES much more secure against brute force attacks. But as we said, 3DES/2 was a common way to go using this combination of encryption and decryption. But if you apply DES twice using 2 different keys, then the brute force attack may still be doable, even though it is more difficult than before, but it's not that much more difficult because there is a technique called the meet in the middle attack. Okay, so now let me open up a whiteboard so I can give you a better idea. Get a whiteboard. Okay. So 2DS, okay, /2 would mean that you apply encryption twice using 2 different keys and get C. So what I want to find is K1 and K2. So 1 to find K1 and K2 used in this encryption from the attacker's point of view. So we hope that K1 and K2 can substantially increase the brute force attack difficulty, because both of them, so you're combining these 2 keys, you get 112-bit key. So if you do brute force, you will do, in the worst case, hopefully you have to do 2 to the 112's power many different trials, and in order to get K1 and K2, right? So you get K1, that's 56 bits, and then you try another one, that's 56 K1 and K2, and then using these 2 and see whether you can break your systems. So in other words, you have a known pair, like a DES. So let's say you have a known ciphertext, so you get known. So I try all possible K1 and K2, then I see whether I get this equality. So if we do, then probably we get that case. So you got to see this many times. But then, of course, if a single key is 2 to the 56, so there is a huge difference. But using meet in the middle attack, we can reduce this complexity tremendously. We can reduce the complexity from 2 to the 112's power to 2 to the 58's power. So 2 to the 58 is not much bigger than 2 to the 56. Okay. Now let's see how we can do it. So let's say I have a known pair. So this is a known pair. So that means I can get D K2 on C should be equal to E K1 of M. So what I'm going to do in this meet in the middle attack is I'm going to apply. So I get all 2 to the 56 many keys. Right, so let's get K1, K2, until K2 to the 56. So I get this many keys. For each key, I'm going to compute. So this is a key. I'm going to compute both encryption and decryption. So this is E, K on M. This is D, K on C. Now, you know M, you know C, so I can run this. So then I will get so let me call this. Okay, so so in order to make it easier, let's call, by doing this encryption, I get X1 using K1. Using K2, I get X2. And then I got X2 to the 56. So for this, I apply these many keys on M. I got these possible outcomes, all of these outcomes. And similarly, for this, I'm going to call it Y1, Y2, and then Y sub 2 to the 56 power. Now, here, so this means, now this is equality. Okay, because of this, we get this. We just don't know which K1 and K2 would be. So then I'm going to compare. Okay, so let's say if K2, if K1, maybe it will have to have something that is equal. So if X1 is equal to Yi, or Y2 somewhere is equal to Xj, then, so this is corresponding to this is K2, corresponding to this is Kj. Then in this case, K2, Kj, now, so I want to, so when I do this, so these K1 and K2 are not the same as this K1 and K2, so let me make that clearer. So I'm going to say two keys. One is K, the other one is K prime. Okay, so that way, so this is K prime, this is K. So then for this K2, so that is a candidate for K prime K. So this is a candidate. So if this is unique, then we are done. We found k prime and k. If unique, then we found k prime and k, which is k2 is k prime, kj is k. But the situation would be that there are so many such candidates, okay? But there might be many candidates, such candidates. So that means we don't know which one it is. All right, so then let's assume I have another known pair. Assume is assume another known pair. Let's call it M prime, C prime. Okay, so now for each candidate, key pair k prime k. Now each candidate, there may be so many. Then I'll apply this on this string again. So I'm going to do is I do mk on m prime. Also, this is e. Do it again. This should be equal to dk prime on c prime. Using the same thing, okay? Using the same table. But then what we need to do is to find out how many such pairs available, how many candidates. Right? So of course it won't be, or any pair will be candidates. Of course it will be much, much smaller. And then, so the key pairs, so the number of such candidate pair much smaller. So I apply on another known pair, and I am going also to get the same thing, also to get candidates. Okay, so so we get candidates, and then get new candidates. Let's call this star, 4 star. Okay, so we can show with probability greater than 1, this is unique. So such candidates is unique with probability greater than 1. I'm sorry, cannot be greater than 1, of course, close to 1. So 1 minus, so let me close, very close to 1. Very close to 1. Hence, with a large probability we find this pairs of keys, okay, with two known pairs M and C. All right, so the complexity, okay, is at most originally you get 2 to the 56, but you do encryption and decryption, so which means you do it 2 times. And then the second round, so this is the first round. The second round, let's say you have how many pairs? Let's call this K pairs. And we already use K, so let's call use a different number. Let's say N pairs. Okay, so this time you do N for each pair. You want to do this many you want to do this many encryption, and you want to do this many decryption. So that's 2 times N. If N, let's say in the worst case, it will just be, so this is in the worst case, right? So N will just be 2 to the 56. So that will be 2 times 2 times 2 to the 56 is 57. So this is 2 to the 58. Okay. So the complexity is much lower, and then you have a large probability to find these keys. So now let's move back to find out. So remember here, we look at this. Okay, so this is how many pairs in the first round, how many pair of candidate keys. So this is the first round. So remember, to begin with, there will be this many keys, but then each block is 64, right? So some of the block under those keys will be the same. So then the candidate pairs is at most 2 to the 112's power divided by 2 to the 64, because that's how many different blocks you can have. So that's 2 to the 48. So that means N is 2 to the 48. Okay, in the previous slide. So then you have this many key pairs. For this key pair, you apply on the second known plain text and ciphertext. So this is a second round. So then you get 2 to the 48 divided by 2 to the 64. Again, 2 to the 64 is how many possible blocks you can have. So that is 2 to the negative 16th. So the possibility of finding K and K prime is then 1 minus 2 to the negative 16. So this is a very high. So this is a very, very high number. All right. So then we know that 2DS/2 is not secure because of this reason. Brute force attack may still be doable. So then, of course, a common way is either 3ds2 or 3ds/3. So this is considered secure.